So I am here to present a skeptical view of dynamics in large-scale brain correlations, since it's a skeptics thing. The talk is in two big parts. The first is actually about dynamics, and the second part is about something that might affect your measurements of dynamics, and that is artifacts that can arise. So I'm going to give the outline of the talk is this. There's a little intro about things that I feel pretty confident about, and so I'm not very skeptical about them. The next question is, can large-scale brain correlation structures reflect changes in state? And I'm not very skeptical about that. I think the answer is yes. One that I think lots and lots of people are interested in lots and lots of different ways is, can we see non-stationarity of large-scale correlation structures in the resting state, suggesting that as you're lying there in the scanner, you're traversing through multiple states, putatively, possibly cognitive states within a session. And as you'll see as I go along, our group is fairly skeptical about this. Are there non-state reasons why someone might see such non-stationarities in their data, resting state or otherwise? And I'm very not skeptical that that is the case, and I think that's unfortunate. And so the last part, we're supposed to say something about the future, so I think I have one slide about the future. So a little bit of intro that I'm not skeptical about. A question could be, is doing this resting state stuff even worthwhile? Are there things that we can learn from it that really tell us about brain organization? So I'd like to outline just one thing that we and many other groups have done, is try to understand a large-scale resting state set of organizational principles that exist. So you can start out with just one seed here, for instance, in left motor cortex. How many times have you seen such a slide? And look at voxels over here on the other side, and you look at the time courses, and they look really like each other, and they correlate. You can also take this set of voxels and say, tell me all the parts of the brain that correlate with those voxels, and they do this beautiful bit of outlining motor-related structures. And so you immediately ask yourself, which we did many years ago along with lots of other people, can you take such a whole bunch of seeds to outline whole bunches of systems? So here is one set of nodes, and I'll go along with Emily. If you have a couple hundred to 300, unfortunately, I'd love to say that it really matters which nodes you put in, because we really worked hard to get this set of nodes. Doesn't really seem to matter that much. And so what you get out, we make a correlation. I know adjacency matrices we've kind of heard a little bit negative about, but what the hell. So we take all of those nodes and pairwise compare them to each other, get the correlation out, and put them in a matrix. You pass them through some community detection algorithm or clustering mechanism, and what you can see is if you then order them by the resultant outcome, you can see that there's a pretty beautiful block structure along the diagonal, indicating that there are sets of regions that really like each other better than other sets of regions. And you can put them on the brain and see that they have a lot of functional validity. So you can take this bunch of red dots here on this matrix and isolate them, and by God, they look amazingly like the default network. That's true of many of the other colored sets of nodes. They seem to have functional validity. We were pretty pleased. You can use, Tom Yo used a clustering approach to this, a methodology that, of course, we think is much less, or is inferior to ours, and even he was able to come up with this beautiful and very similar structure. So one thing that I think is clear is there seem to be a number of reasonably separate systems, and they can be reliably described on the basis of simple large-scale brain correlation structures, and they cover much of the cortex. So This is just to set a baseline of my non-skepticalness as we go along. Second question, can we use these large-scale brain correlation structures to answer the question, can they reflect changes in state, or are they functionally driven only by anatomy or by some underlying, non-mutable structure? So let's think about state for a moment, and I'm going to constrain what we're going to talk about in terms of state. So if I'm in a working memory task or I'm in a no-go, no-go task, I would think of those as different states. If I'm lying there like a lump in a scanner, those two task states are different from the rest state. So I think of those as real state changes. How about levels of arousal, real differences in levels of arousal, say sleep versus wake or multiple levels thereof? I think those are real differences in state. Something that we haven't looked at all are differences in mood. If you are excruciatingly depressed versus in a really happy manic state, those I think would be really different states. Things that I don't think of so much as being differences in state, I thought about dinner because I was getting hungry before I came up here. I don't think of that as particularly being a change in state, or if I see a visual stimulus or somebody walking out of the room during my talk, I don't think of that as a change in state. So what I'm going to be talking about from here on are these kinds of states. And so my first question is, can states of the kind I've just described be seen in these large-scale bold correlation structures? So I'm not talking about states that could be found at a shorter time scale or a longer time scale, across sessions, or something that you might be able to see on the hundreds of milliseconds time scale as you might with EEG and MEG. I'm really going to be agnostic about that. In fact, I'm pretty sure there are non-stationarities in EEG and MEG data that are invisible to functional connectivity metrics. So in thinking about let's talk about goal-driven tasks for a minute. So two things would have to stand for us to believe that you could see changes in states with these effectively correlation matrices. First, are task correlation structures different from rest and from each other? And if so, could we detect these things in ongoing correlation measures? So could we embed such differences within an ongoing signal and be able to detect them? So what about goal-driven tasks? So Katerina Graton has a recent publication in which we looked at 3 different tasks and their relationship to rest and looked at their correlation networks across different task and rest states. So although these are amazingly similar, so if you take the group average rest matrix and the group average task matrix, averaging the 3 tasks together, they look amazingly similar to each other. There'll be a test you're going to have to point out where all the differences are between these things, which is incredibly difficult because they correlate with each other at about 0.96. So the differences between them are amazingly subtle. On the other hand, by using an object-oriented data analysis approach, all of these tasks are different from rest, each individually, and they're all significantly different from each other. So a place to view is right here. This is the somatomotor. Body, arm, hand is actually different across the tasks and actually produces a large scale of dissimilarity between the matrices. So the other question that I ask is, if we embed such small differences within an ongoing signal, could we see them? So one method to find state changes in time series or in correlation structures like this is to look for changes in stationarity as measured by multivariate kurtosis. Now, this was first described, which I'd never heard of in my life, by the way. This was first described by mathematician Mardia in 1973, so this is called multivariate kurtosis in the sense of Mardia. And the question is, if such tasks were embedded within REST, then the changes in correlation by the structure produced by the task should produce changes in multivariate kurtosis. So fortunately, the original experiment was looking at state differences when you embed tasks within task versus REST, mixed block event-related design. So we had a set of REST scans, and then we embedded a task with REST, task, REST, task, REST. And when you look at this, the changes, although as I showed you, the changes that the tasks produce are very subtle, you actually get a change in multivariate kurtosis where it is bigger in all three of the tasks relative to REST. So what this is telling us is that this multivariate kurtosis measure can find changes in state in an ongoing signal. Another possibility, what about changes in arousal or drowsiness? So Tagliazucci and Laus did an incredible, I think, extensive analysis of looking at sleep state during resting state scans. And they had a lot of results. The one that we're going to take here is that you can actually estimate the probability of being in different sleep states during a scan. So in collaboration with them and a couple of incredibly bright graduate students, Tim Lauman and Anish Mitra, they came up with a sleep index. And what the sleep index does is tells you how much of a scan are you spent in a drowsy versus an awake state. So when you do this, the more light sleep during a scan leads to higher kurtosis. So what this is saying is as you mix sleep in with wakefulness, you drive up the apparent non-stationarity within the scan. So both tasks and sleep show apparent state changes, non-stationarities, and ongoing large-scale correlation structures, which immediately leads to sort of the next question. So do we see such non-stationarity of large-scale correlations in resting state, suggesting that people are traversing through multiple states within a session? Now you know, if you've ever been in a scanner, like Russ has, 100 times, you think about different things when you're in there. If you're a guy, you think about food and sex and other kinds of things as time goes by. So it kind of feels like maybe you're in a bunch of different states. So is that evident when you look at resting state scans? So just to give you a sense of what this looks like in real time, this is the correlation matrix just as time goes by. And so it looks incredibly dynamic, like all kinds of things are going on. So you can actually take a sliding window and say, take 100 seconds and move it along throughout the course of an entire scan, and look at the correlation between two regions. And I'll tell you that the full correlation between these two regions, if you take the entire scan, is essentially nothing. But if you take a window and slide it along across the scan, what you can see is that the correlation between these two regions varies a whole lot, from highly positively correlated to highly negatively correlated. But on the average, it's not much. So can we find a baseline to make a kurtosis measurement that we can then compare the resting state data to and ask, is there extra kurtosis beyond a sort of baseline model? So what we did is we took a bunch of resting state-like time courses, We gave them the covariance structure of the data itself, so how they arrange themselves into their communities and non-communities. We took the exact spectral content that exists in real data, so now we've got a model that's determinedly stationary. There's no states in this model whatsoever, but there is the variability that I just showed you from a sliding window. And so just at this level, it looks like real data, which it should because we built it off the real data. So when you compare the model to the actual data, you really don't see much extra kurtosis in this. So the multivariate kurtosis is saying there is really not a heck of a lot going on. But people have been looking at this sliding window stuff for quite a while now, and various and sundry other ways of trying to look for state-like outcomes in resting state data. So one way to do this is to look at the covariance matrix at each of the windows, and then do some sort of clustering on the windows themselves. And by God, when you do that, you get these beautiful state-like different looking matrices that appear to recur over time, as if people are marching through a set of states. So what's wrong with your data, Petersen? What's going on here? Here we're looking at clustering of this kind of data, and it looks like there's all kinds of differences in it. And by God, if we look at our data, looks just like everybody else's. So if you do the same sort of clustering analysis, you can see beautiful different, quote, states in the data. But what about the simulation? So here's the real data again. And here's performing a clustering analysis on the stationary simulation. And this, I have to admit, was the most surprising thing in all of our work on this. Not only do states appear, they're these states that you see in the real data, the quote states in the real data. So something about the ongoing time variations, even in a very stationary model, will produce this sort of clustering. So can we fully claim non-stationary and resting state? And we have to say no. But the way we've looked at this and the way we've measured it make a hurdle for people who want to make such claims. So I love this. Our math collaborator, who looked at us like we were fools because we didn't know multivariate kurtosis in the sense of Mardia, which has been around for 40 years, he came up with this line, which I love. Although the emperor may be wearing clothes, in other words, there are non-stationarities in states, if the clothes exist, they exhibit all the expected properties of invisibility. I love it. So in our hands, there's not strong evidence of much, if any, non-stationarity in our data in an ongoing resting state. Well, are there other reasons why such non-stationarities might be seen? And there are a couple of obvious answers to this. The big two that I thought of, and Tim thought of, and the other people on the Dynamics project thought of, is there are no artifacts that produce systematic, spurious changes in correlation states. The first is frank motion artifacts in terms of motion spikes, and the second are related global signal artifacts. So this is probably the best single subject we've ever had in our data set. To give you an idea of what this is here, this is a trace of the movement, and notice the scale, it's 2 millimeters. So this person produced one tiny little movement in this entire scan, which was maybe 0.2 millimeters. But what that does is it produces a spike in the imaging data itself. So these are time courses across time in a whole bunch of voxels. and you can see that this tiny little movement was related to a white, black, white stripe in the data. So the thing that we're measuring here is what's called frame-wise displacement. It's how far, when you do motion regression, does it think that the image has moved. So this person didn't move. So can motion spikes cause apparent non-stationarity? So this is the data that I showed you earlier if we don't do corrections for frame-wise displacement. And what you can see, as frame-wise displacement goes up, apparent multivariate kurtosis goes up. If you then go ahead and do motion artifact rejection in terms of taking out the motion spikes and interpolating the data, what you get is what I showed you before, which is essentially no kurtosis. What about the other thing, this global signal artifact? Well, while this isn't the best subject you'll ever see, it's not a hugely horrible subject. This person would have ended up in your data. But what you can see is going along here, besides motion spikes like here, there can be these long, ongoing, what we think of as global signal artifacts throughout basically the entire gray matter. Do you really think that wouldn't produce an apparent non-stationarity? Well, we think it would. Now, thankfully, global signal regression and dealing with motion spikes can remove many of these sorts of artifacts. So here is a high versus low motion group without doing any noise reduction. If you take out the global signal, you take the number of differences down very small. If you then scrub it for motion spikes, you can take this basically down to chance. So you can get rid of things by doing the things that you need to do to get rid of the motion-related artifacts. Okay, wow, 2 minutes. Okay, so global signal regression, as I heard this morning, is highly controversial. I honestly don't understand why. But there are a couple of arguments against global signal regression that I'd like to address just for a minute. The first is global signal regressions create negative correlations that aren't there. And that's true to an extent because it will zero mean your distribution. But if you have low movement subjects, there are certainly negative correlations in your distribution. And I will tell you, don't have to believe me, those are things like the default mode network with basically all of the rest of the brain, just like you would guess. But more importantly, if you don't do it, you artifactually move this distribution to the right significantly. And so you're worried about taking away or putting in negatives that aren't there. What about taking away negatives that are? Problem one. The second is there are simulations that show global signal regression distorts time course relationships, which is certainly true if you have only two signals and you regress the mean of the two weakly correlated signals out, you will produce distortions in the apparent time course. But what if you had a lot more differently related time courses? The answer is, as you get to a closer number of signals that might relate to a brain, the amount of distortion you get is very small. For other motion-related issues, I think there's a fabulous paper by Sirik, and Satterthwaite's the senior author. Please go and read this paper. Please. It is a fabulous paper about all different kinds of denoising strategies. I have to put this in. So I see in papers all the time, especially ones that I review that I subsequently reject. Global signal regression is controversial, therefore I'm not going to do it. So this is very similar to me in construction too. Evolution is controversial, particularly in Kansas. Therefore, I'm going to teach only creation science. Okay, So, I'm going to skip my future and say, do large-scale brain correlations reflect changes in state? It certainly appears to. Do we see this in resting state? In our hands, not so much. Are there other reasons someone might see non-stationaries in their data? Yes, particularly artifacts. And do studies of states in large-scale correlations have a future? And I have to say maybe, because people tend to use tainted data and excruciatingly difficult ways of trying to get around this. So, thank you.